Okay, so tonight's talk is in-memory computing, SoC with multi-level RRAM to accelerate AI inference. So our speaker is going to be Wenbo Yin, SVP of IC Design at TetraMem. So please silence your cell phones. Sometimes I forget that as well. About the San Francisco Bay Area ACM. So we're a local professional chapter. We were founded in 1957, so we've been going a bit longer than meetup.com. We are a nonprofit focused on promoting knowledge of modern computing. We want to create community, support networking and hiring. There's a $20 annual membership. I don't think we've raised that since I got involved in 2006. We have upcoming talks on our meetup site, and we have past talks, about 200 recordings or more, maybe. I think it's up at 240. I haven't counted lately, of our more recent talks on our YouTube channel. So there's quite a lot of content. And so we have 2 monthly meetings. There's a general computing meeting, typically the 3rd Wednesday of the month, and a data science SIG, typically the 4th Monday of the month. If you like us, give a 5-star review on Meetup. We have a couple of sponsors we'd like to thank. There's a location sponsor here for Valley Research Park. So they have R&D suites for rent here in Mountain View. So they support 60 growing startups that enjoy the benefits of the science-oriented facility, modern office space, conference rooms, break rooms, and a good co-working community. Another sponsor is RXM. They do cloud native and AI training and consulting. So sometimes they could, if your company needs training in Munich, Germany for a week on Kubernetes, advanced Kubernetes, then they can do that. That's custom for a group or things like that. So go in depth and do very specialized training. Another sponsor is FrontEgg. So they help with out-of-the-box low-code identity platform. So you can do chat in Zoom. I'll be monitoring questions on Zoom, and occasionally I'll raise my hand and ask questions on behalf of the audience to the speaker. And also for the speaker, please be kind to him. Don't be tempted to go into like a 3 minutes of context and then a 4-part question, because we're doing this recording for YouTube as well. And I ask the speaker to repeat the entire question. So if he's not going to remember it, you have to be shorter. There's no problem. Raise your hand a second time. So have medium-sized questions that the speaker can remember. And also, speaker, I'll ask you to repeat, because the speaker on your laptop won't pick up the audience asking the question. So if I do this kind of gesture, it just means please repeat the question. So we have a call for volunteers. I found one already today, just talking to some people. Raise your hand. Hey. So we have about a dozen volunteers that run this nonprofit organization. So some people have different strengths and areas that they can contribute. So my focus is on inviting the data science speakers or that related events. I've been doing that since about 2008, but I'm one of many people that contribute to it. Other people help in a lot of different areas. We have an honor system jar for food. Liana, is the honor system jar out? I think it is. So upcoming ACM events. So less than a week away, Monday, here at VRP, we'll have a co-pilot for social promotion. So Dr. Boris Galitsky will be coming from out of the country and giving a talk here. Then Wednesday, August 20th, they'll be designing for scale, reliability, resiliency, and real-world lessons. So this is going to be a general computing talk, not an AI talk. So we have some talks of each kind. The green text is for the data science talk. Then in August, we have When Bias Goes Viral, protecting your brand from biases in generative AI. And then later on in September, it might be moved to Tuesday, deploying and scaling it large language models in the enterprise, architecting multi-agent AI systems, integrating vision, data, and responsible AI. So that sounds like a very good talk as well. I haven't posted that one on Meetup yet. I probably will by the weekend. So now to introduce tonight's speaker, it's in-memory computing with a multi-level RRAM to accelerate AI inference. So he'll be talking about introducing multi-level RRAM for cell for in-memory computing, explain how it accelerates neural net inference apps, increase precision, accuracy, and energy efficiency. It was recently published in Nature and Science. He's the SVP of IC Design at TetraMem. He leads design efforts, including mixed signal circuit design and NPU architecture. He joined in 2019. So please help me with an applause to welcome our speaker, Wenbo Yin.
Thanks, Greg. Is it audio okay?
Yes.
Okay, great. Yeah. Thanks, Greg, for the warm introduction, and thanks ACM and Liana for inviting me. ACM is a very prestigious and highly influential society. It's my great honor to share some of my experience working on in-memory computing in this talk. And especially I'd like to highlight, I'm also very honored to give this presentation, followed by a recent presentation from Tom Coughlin, who talk about various kinds of emerging memory technology in the context of a storage and data center. So if you haven't listened to Tom's talk, I highly recommend you to check out the recording on YouTube, where he talk about all kinds of emerging memory technology. If you can first. Okay, actually I've got it, but thank you. Yeah. I highly encourage you to check out our past the past presentation by Tom Coughlin, who talk about different kinds of emerging memory technology and their application for a data center and AI. And in that presentation, you'll find that he talked a broad range of a new memory technology. And in this particular presentation, I'll be homing into one of them, which is called the RRAM, also known as the resistive memory, and its application for in-memory computing. So I'll start with a safe harbor statement. So this is not intended, not intended to give an accurate estimation of everything that we do in the future. These are general looking estimates of our best guess at the current stage. And if any of these presentations are inaccurate, or if things change, we will, so please bear that in mind. I don't think I need to, there's no way to overstate the importance of AI. The explosion of AI adoption is driven by virtually every sector, and it fuels the demand for both general purpose chips as well as specialized accelerators. So the past few years has really been very exciting for us in the hardware industry. So for the personal device, the industry is pushing, to deliver AR/VR headsets, and that requires a lot of energy efficient chips. And innovation in the AR/VR, it promises a new experience in entertainment and productivity. However, for AR/VR, a lot of times more compute is required to really create the immersive experience that blends the physical space with the digital content. We also have a Gen AI. I'm sure most of us use ChatGPT or one of its competitors. And we're developing ever larger AI models around the world with more sophisticated algorithms for text generation and video generation. However, as those algorithms become more complex, we see a bigger gap between the data, the algorithm, and the hardware computation capacity. And we're only getting started. Currently, we're seeing an explosion for a robotaxi that's leading. Robotaxi companies are leading leading technology companies are deploying them on scale across the world, as well as we're beginning to see the takeoff of humanoid robotics. So all of these trends require more compute, more memory, and more importantly, they require more sophisticated AI algorithms that need to be efficiently run on each device. So the explosion of AI is fueled by all kinds of innovation in the data generation and the marking in the neural network algorithm, and also in more efficient computing hardware. But among the three, I think the hardware has clearly become the bottleneck for both training large models as well as deploying them on each device in an energy efficient manner. So just to give you an idea about the growing gap between algorithm and hardware. So in general, our data, which is our ability to generate data or capture data, either representing real world or digital data, is growing at a rate of approximately 100 times a year. The algorithm complexity represented in some of the largest AI models. So think about GPT, Cloudy, Llama. the complexity is growing at approximately 10x per year. But our compute power in terms of both CPUs, GPUs, as well as memory capacity, they are still growing, but they're growing at a much slower pace. So by and large, not counting for the reduction in the accuracy, so things like going from 32-point to 16-point accuracy, things like going from floating point to integer. So not counting the reduction in model accuracy and precision, our conventional processors have only been getting better at the rate of approximately twice every year. And that's a pretty good advancement. But it does leave a larger and larger gap between the algorithm and the hardware. And as we can see, at a lot of times, the speed at which we innovate our large language models is limited by how much hardware we can deploy, as well as how much electricity we can supply to those data centers. And as you guys may notice, some of our leading AI companies have been invested very heavily in energy generation. Amazon, Google, Microsoft have all invested in nuclear power plants. And right now, if you look at some of the data centers that are actively being built, 5 years ago, we talked about data centers in terms of exaflops or petaflops, just like we talk about TOPS or gigahertz for CPUs. But now when we talk about data center, we talk about them in the metrics of gigawatts. So using energy as a measure, I think there's some echo. Yeah. So using energy as a measure for data center performance is clearly indicating that we need more energy efficient chips. And we're only going to be able to develop AI models as well as at a pace if we can develop better or more energy efficient chips. So obviously, we are not the only company working in these problems. There's a lot of ongoing innovations to make the hardware more efficient. But we believe the fundamental challenge exists in the approach of conventional digital computing. So let's look at some of the very promising solutions. One problem is called the high bandwidth memory, abbreviated as HBM. So in high bandwidth memory, we deem to stack multiple dies together, essentially multiple dies of memory on top of compute dies. And while it reduces the physical real estate and it reduces the distance that the electrical signal has to travel between the processing unit and the memory unit, but there's still a bottleneck. The bottleneck is still there that we have to move data back and forth between the compute and the memory. Furthermore, 3D stacking also limits the thermal dissipation, and it increases exponentially the packaging cost. There's another solution, which is basically more on-chip or more on-die memory. This is one of the reasons that our data center chips have gotten more and more larger in size and require more and more advanced CMOS technology nodes. But there's only a limit in terms of how big we can make the chip to be before we're limited by a low yield, as well as the so-called lithography reticle limit. So basically, there's a physical limit of around 800 millimeters squared per chip, and this is dictated by the manufacturing equipment at the foundry. And obviously, this can be improved, but only at the scale of tens of billions of dollars of capital investment. Last but not least, advanced process nodes do continue to deliver better energy efficiency, as well as information density. However, SRAM scaling has slowed down significantly, and some technology nodes in certain leading foundries have essentially stopped. So what that means is that although we're able to build chips that packs more transistor and can deliver more raw theoretical performance, we're still limited by only being able to turn on part of the chip at one time in order to not overheat or in order to not run into the traditional memory bottleneck. So we believe that the current computing architecture is very inefficient for AI. In fact, 90% of the energy for our overall GPU system is spent moving information from one chip to another, and this translates to significant data loss, significant power loss from the data transfer in the bottleneck between the processor and the off-chip memory. And this is and power is everything in data center. In one of the articles published by Google, the total cost of ownership of operating a data center is linearly proportional to the amount of power that the chip needs. Because for every watt of power the chip consumes, not only you have to pay 1 watt of electricity to power the chip, you have to essentially pay another watt in terms of cooling to remove the heat from the chip. So for every watt the chip consumes, the data you essentially need to pay 2 watts of electricity. So at TetraMem, we believe that in-memory computing can fundamentally address these challenges. And the reason is that the IMC chip can achieve high-density storage and efficient matrix multiplication in the same physical location. Furthermore, this architecture is inherently friendly to parallel computing in terms of data and the thread parallelism. In addition, IMC can also lower latency for large vector matrix multiplications, which accounts for about 80 to 90% of artificial network workloads. And this much higher efficiency in matrix multiplication enables both a reduction in memory bandwidth as well as an improvement in latency. So in the graph on the right, this is an example of some of the work in the industry. In fact, this is not published by us. It's actually published by other researchers. But there's an increasing consensus that in-memory computing can reduce the inference energy by about 2 to 3 orders of magnitude compared to existing conventional systems. So how does it really work? So let's zoom in a little bit to a little bit lower level on the cell and on the hardware device level. So suppose that we need to do a multiplication or addition. So the diagram on the right is how it will be executed in a traditional digital system. So this is essentially a full adder. For each full adder consists of various logic circuit as well as a memory. Each memory cell consists of 6 transistors, and using multiple full adders together, we can build an adder tree.
I thought I was.
Yeah. So using thanks, Greg. So using a different combination of SRAMs and adder cells, we can build a full adder circuit, and we can build a shifter and a multiplier. So this gives you an idea. It kind of takes about on the order of a few hundred transistors in order to perform a matrix multiplication. So in-memory computing means we actually only need a single, well, technically 2 devices, a single transistor and a single RRAM cell to perform a single vector matrix multiplication. So the transistor is used for selection. It basically turns on and off a device. And the input, in single-bit digital input, can be applied to the gate of the transistor that turns on or turns off the cell. So weight, which is the number that we're trying to multiply, will be stored as a resistance or the conductance in the RRAM cell. And this can be stored actually in the analog domain, which means that in each cell, in each RRAM cell, we can store multiple bits, 2 bits, 3 bits, 4 bits, 8 bits, and even more. So a single cell that consists of a 1T1R, only 2 devices can perform a single scalar number matrix multiplication, replacing hundreds of transistors in a conventional digital circuit. And this leads to higher energy efficiency and lower cost. So what are some of the advantages of chips that are built using this architecture? Well, first, it eliminates the bottleneck. Why? Because in addition to having to move the weight of the neural network from the DRAM to the processor, we now have this high-density storage device where we can store the weight on the computing Memristor itself, meaning that no more weight movement, no more volume bottleneck, and significantly less energy and a faster inference speed. Secondly, we can significantly accelerate computing throughput for inference mode because all these weights are stored in a dense matrix that can perform vector matrix multiplication parallelly using physics laws like the Kirchhoff-Curry's law or the Ohm's law. And lastly, this technology is scalable to advanced technology nodes. So in our 2019 Nature Technology publication, we have shown that this RRAM technology is scalable even to 2 nanometer dimensions. So you may ask, well, if in-memory computing is so promising, why is it not in every device already? The key is really to find a suitable memory device for IMC that can really meet the different requirements, the application, the PPA, and the product level requirements. For example, application requirements may include for in-memory computing, we need a device with high IV linearity for an analog in-memory computing approach. It also means we need a multi-level cell to avoid the expensive weight combination, and the cell must pass all the reliability and the retention spec that's needed for the lifetime of the product. So there's a lot of memory device out there, SRAM, DRAM, non-volatile memory device like a NAND and a NOR flash, MRAM, ferroelectric RAM, and RRAM. There's a lot of memory device out there, and they all have their place in the memory hierarchy. However, many of them are actually not suitable for in-memory computing. And at TetraMem, we believe the best device for in-memory computing is the multi-level RRAM, or otherwise known as the resistive RAM. So let's look at some of the other memory device for in-memory computing, and let's briefly discuss their advantages and the disadvantages. So broadly speaking, memory device can be categorized in terms of a volatile device versus a non-volatile device. Volatile means it loses its energy, it loses its stored value when it's powered off. Non-volatile means it retains its stored value even without power. So for volatile device, we have a DRAM, and which is basically essentially most computer memories are made out of, and SRAM, which is what most CPU cache or GPU cache are made out of. So these are great devices. However, they're only memory, they're only binary, meaning that they can only store a single bit of information per device. And because of their volatile, they need to be frequently refreshed in the case of DRAM, or in the SRAM, they need to dissipate leakage power in order to keep retaining its information. And this is great because they're very fast, but it means that we're limited by how much on-chip memory we can store, which means we're limited by the size of the neural network that we can run. And as long as we run out of on-chip memory, we have to have off-chip memory, and off-chip memory access is around 100 times less energy efficient than accessing information on-chip. There's also a lot of non-volatile memory. For example, NOR flash is very popular. However, NOR flash is a very expensive process. It requires 9 to 6 mass added to the front of the line process. And it also has scalability issues. In fact, all commercial foundries have stopped developing NOR flash below 28 nanometer because the industry has moved to NAND flash. MRAM is also a great emerging non-volatile memory technology that has a very good retention and endurance. However, it cannot be used to store multi-level, which is needed for analog in-memory computing. And it is also subject to magnetic tunneling issues, which means that the device we built is really sensitive to magnetic field, limiting its application. And lastly, PCRAM. PCRAM is also a very good non-volatile memory. However, it is subject to conductance drift and the thermal-induced conductance variation, which means that it is very difficult to manufacture in a large-scale volume production. So at TetraMem, we use the so-called computing Memristor for in-memory computing applications. So what is computing Memristor, or otherwise known as So a computing Memristor is actually the fourth fundamental passive device. And this actually Leona, would you mind to mute? Would you mind to mute your Zoom? Yeah. Would you mind to mute your Zoom? Okay, great. Thanks. Yeah. So computing Memristor is actually the fourth fundamental passive device. The reason it's the fourth fundamental passive device is actually predicted by a professor Chua at UC Berkeley in the 1970s. So he basically wrote the electromagnetic equations for all the passive circuit elements. So if you write the voltage, so if you write the electric field and the charge equation, you actually get the resistor, the capacitor, inductor. They're all familiar circuit elements that have been used widely, but due to the symmetry of the equations, there's actually a fourth fundamental element called the Memristor, which he predicted, and he predicted the model, the circuit and the mathematical model of the Memristor. He predicted its behavior just because of the symmetry of the electric field, and he said that this will be a groundbreaking device once we figure out a way to make it, and we did about a couple of decades ago. So essentially, a Memristor is a device that is essentially a Memristor is a device that can store a value in terms of resistance or in terms of conductance, and the resistance can be changed using a combination of a voltage and currents. So the mechanism in which it develops this resistance is through a conductive filament, which acts as a kind of a bridge that can be used as a resistor. And this conductive filament can be made narrower or wider, which changes the resistivity by applying a current or voltage through it in a different amplitudes or directions. So this is actually very similar to the functioning of a human neuron, and that is why a lot of research, including TetraMem, has been using this for computing systems that are much closer to how our brain operates. So with the control of the conductive filament, the ion concentration, and the height, we can achieve multiple levels of resistance, meaning that this is how we can use a single cell to store multiple bits of information. Until recently, this device has not been available in the commercial foundry, but that time has changed as TSMC's director, Kevin Zhang, said in last year's SCC, the emerging memories have finally emerged.
If you want help, the Zoom annotations can be minimized or
Okay.
put away.
Yeah. Thanks.
Yeah.
So here's a little bit operation principle of in-memory computing now that we understand how the memristor works. So we first need to program. We have an array of memristors. This is also known as a crossbar device. So we first need to program the crossbar device in a fashion where each device corresponds to the weight of the neural network. And then a convolution operation or a math-mul operation needs to be flattened and mapped into a vector input. And the vector input can be applied to the input of a crossbar array using a series of digital to analog converters, DACs. And these inputs are applied to different weights of the neural network, so which results in a summation current that is being developed on the bit line. And this bit line in the analog domain is converted back to digital using the analog to digital converter. So in a nutshell, for a convolution operation, for the weight is unrolled into a weight matrix, which is mapped onto this crossbar array. The weight of the neural network is mapped into different conductance level, which is stored in terms of conductance or resistance on the RRAM device. The input of the neural network will be driven to the input of the crossbar using a series of voltage or pulse, and the output of the vector matrix multiplication is summed up on the bitline direction, which is converted back to the digital domain if needed, using a column parallel analog to digital converter. So this architecture means we have a very efficient processing for inference neural networks because number one, we no longer need to load the weight from external memory. They are all stored in this computing RRAM device. There's no memory wall. Number two, we can load the same input into multiple filters in parallel. It significantly increases the input reuse. Number three, because the size of the crossbar can be made very large, usually a 1K or around the order of 1K in each dimension, it means we can perform a very large matrix multiplication in parallel. Number three, because we can multiply a very large matrix in parallel, we minimize all the intermediate load stores to the conventional memory. And lastly, because we can achieve a very high precision, which we'll talk about later, which are architecture level innovation. So I talk a lot about the multi-level RRAM and how we can use this Memristor to achieve a multi-bit storage. So you may ask, well, how good is this multi-bit RRAM? How many bits are we really talking about? So in our 2023 Nature publication, we have demonstrated 11 bit per cell. Yes, 11 bits per cell means a single cell can store 2 to the power of 11th, which is more than 2,000 levels in a single element. And that can only be achieved through a combination of a material and a device engineering, but also electrical programming and algorithm. So in fact, in this Nature paper, we've actually invented a technique to improve the noise performance of the cell beyond what is conventionally known possible, using a combination of electrical techniques so that the unstable filaments for RRAM can be reduced or eliminated. And furthermore, we have demonstrated with a very good retention and endurance on this RRAM device that really paves the way to a volume production. So this is cover. Yeah. This is a of our Nature article, and this is a silicon wafer in which we took the measurement and able to and was accepted in this prestigious Nature publication. So as you can see, this is not a kind of a lab device. This kind not like a science project. This is a commercial foundry, commercial wafer with a very large memory array, extremely high density, and extremely good and retention and endurance. For those who have a lot of experience working with analog chips, we may also ask, well, it's great that we can do multi-bit, but analog computing cannot achieve good accuracy. It cannot achieve a similar accuracy as digital because there's always issues like a noise, like device precision, like a variation, like a circuit sensitivity to temperature. And you will be correct if we didn't have to innovate on architecture and the algorithm in this front. So instead of, we recognize the fact that for analog processing, there will always be some noise. And on a fundamental level, a lot of noise, like a thermal noise or KT over C for a capacitor, a lot of these are just physics. They are unavoidable. But on the architectural level, we have techniques that can go beyond the barrier of a single cell performance and really demonstrate application level accuracy. So this is a follow-up article, which was published in 2024 in the journal Science. TetraMem and our university research collaborators have actually demonstrated floating point level accuracy using a relatively low precision RRAM device. So in this paper, we showed that by using different cells to kind of compensate for the residue in the programming error and the device imprecision, we can achieve the same accuracy for a scientific computing, which is demonstrated using solving electric field problems, using the analog in-memory computing using 8-bit cells. So a series of 8-bit cells that can cancel each other's variation and inaccuracy can actually achieve the same application level accuracy as floating point or as the software solutions. Yes.
And so this means that you have to sort of perform the operation multiple times?
That's right. So the question was
passes over the data.
right. So the question was, so this means we have to perform the operation in multiple times through multiple paths. And essentially the answer is yes. If we find that if in one iteration the accuracy is not sufficient, we can map the residue and use a second iteration to further improve it. And if you look at our this science article, using just an 8-bit cell, we cannot get floating point level accuracy with one pass. It actually requires 2 to 3 passes to get to the same precision.
And to achieve good enough accuracy for your application, how many passes are you thinking about?
Right. So the question was, how many passes do we need for the application? In fact, in most of the applications that currently TetraMem is addressing, we find that just one pass with 8-bit integer accuracy is sufficient. This is because most models and the machine learning framework supports native quantization to 8 bits. This is something that from edge models to large language models, like even DeepSeek uses a lot, where we see increase in reduced precision can reduce the computing workload. So integer 8 is kind of the standard for many models. So our chip natively supports integer 8. However, if there are certain models for certain applications, or there are certain layers of a model that require higher precision, like a fully SP32, then that generally requires a multiple pass, like a 3-pass.
So only 3 to go from 8 to 32?
Yeah, so the question was only 3 to go from 8 to 32. The answer is kind of, and the fact that it's not so precise because we're not trying to build a calculator. So definitely 3-pass of 8 bits will not get you, if I were building a calculator, it will not get you the same accuracy as a floating point 32. But in this particular application, the problem we were trying to solve is like the electric field equations, and which we found the 3-pass is sufficient. There could be other problems where we need more pass, and that definitely that's definitely possible. Yeah, thanks for the great questions. So in the true analog approach, so we have the weighted sum of a multiple device. Is used just a little bit more detail on this. Seems like there's a lot of interest in this work. So in the true analog approach, we use we use a weighted sum of multiple device to represent one number, and the subsequent program device can be used to compensate for the conductance error of the previously programmed device. So eventually we can make the final value arbitrarily precise by adding more device with a reasonable overhead. So for the first time, our chip demonstrated the same precision as the software running the complex machine learning models. And we have developed that into an SDK and package it into a system. So this is known as MX100. This is the first 8-bit cell for an in-memory computing chip. And this is actually available through our developer program. So this is in this chip that is made in 65 nanometer technology. It can store a neural network of up to 620K neural parameters that includes a natively integer 8 with support. In addition to the analog NPU, which we talked a lot, there's also an on-chip RISC processor for easy program and SDK deployment. In terms of VMM energy efficiency, this chip we can get more than 20 TOPS per watt in integer 8. And for those who's familiar with AI systems, this is around similar or better energy efficiency as some of our existing chips can get in the digital, like a 3 nanometer or 5 nanometer. And we're getting better performance in the 65 nanometer at the integer 8 level. So this really demonstrates the extremely superior energy efficiency for in-memory computing, even that the chip is developed and manufactured at an older technology node. So the total power of the system is around 30 milliwatt, and we have developed the SDK that includes the NPU driver, ML compiler, ML quantizer, and the virtual platform.
Question. Is there support for TensorFlow or scikit-learn or different numerical libraries to run on this, or that has to be developed from scratch?
Right. So the question was the support for a numerical library like TensorFlow. And we'll walk through our software development flow later. But the short answer is essentially we currently take an ONNX input. So if you have a model in the TensorFlow or PyTorch, they can be exported to ONNX format.
Okay, so you can export models to that format. Can you train models, or it's just for inferencing?
That's a great question.
Go ahead, repeat.
Yeah, sorry. The question was, can we train models, or is it just for inferencing? So the answer is, as a chip, this particular chip is just for inferencing. Because we mentioned that we natively support 8-bit quantization, which is sufficient for most inference applications. However, for training, we probably need a higher resolution. So in general, we do not train. However, there's an exception. The exception is there are cases where a model will lose accuracy after quantization, in which case we do have a development flow where we can work with our customer to do the so-called quantization aware training, which means to factor into the quantization loss during the training process, so that when we later do the quantization, there will be a very little accuracy loss. So we do have a flow that can perform a quantization aware training. But other than that, we use existing pre-trained models. So in terms of the application, so we have multiple on-chip demos using our MX100 chip. For example, we have a digit classification using the MNIST network. So think about if you're sending a letter through the mail, you're writing some address. So that address as a postcode is scanned by an automated machine that and then routed to the system. So MNIST is a relatively simple network. It's a 3-layer CNN model, and that can be easily implemented in one NPU. Another very good application is the so-called pupil internet. So this is something that's commonly used in a lot of AR and VR device. For AR and VR headset, we need to track the gaze, or basically essentially the location of the pupil in order to identify what you're looking at, so that the headset can deploy the right content and the right immersive experience according to where your eyes are looking. So this needs to be tracked at a very high frame rate, as well as a very low power. This is something that our chip do very well. For the pupil internet, the kind of accuracy metric is the normalized coordinate for the mean squared error. We're able to get a very good normalized mean square error that's comparable to software solutions. We also run this on multiple other networks, for example, Visual Wakeboard, which is used in a lot of camera-based like surveillance applications. Think about your Alexa Ring or secure doorbell. You want to be able to detect whether a person or another object has entered into the frame, and once they enter frame, you may want to capture the image or trigger alarm or do some subsequent face recognition. So Visual Wakeboard, we're also able to demonstrate this slightly more complex 5-layer CNN models. It's a little bit larger model, so that's why we need multiple NPUs to be able to deploy this model. And we also did this for audio models as well. So like a keyword spotting in the speech clients dataset. So think about once wake up for a smart IoT device like Alexa, Google Home. So those devices that needs to be interacted using a voice. So this neural network detects the voice command, as well as to do the noise filtering in the case of like reverberation or echo. So in all of these networks, we're able to take an existing standard state-of-the-art network, deploy it onto our NPU in a very efficient manner. We're able to achieve comparable accuracy with the digital solutions. So all of these accuracy are quoted, and we're able to get really good energy efficiency. And lastly, there are like a real world use case that can be easily deployed through our SDK.
So when you, how do you build multiple NPU devices?
Right.
Put them in an array and put them in a larger printed circuit board?
Right. In this case, this MX100 chip, it has 10 NPUs. So anything that require less than 10 NPUs, they can all be run on the same chip. And this will probably be a good way to scale the chip. Usually there's a lot of applications where one NPU is not enough, so we need to build many NPUs, and then we have to have the like a kind of a power gating and the clock gating to make sure that those unused NPUs can be turned off when running a smaller neural network. But obviously, there will come to a point where, regardless how many NPUs we build in a chip, there's always a bigger model that cannot fit in a single chip. In that case, you can kind of daisy chain multiple chips together using our standard protocol that can parallel run, or each chip runs a part of the network.
And what is the topology of a multi-chip solution.
Right. So the question is, what is the topology for a multi-chip solution? This is actually a little bit. The answer is it depends. What it depends is that it depends on the size of the network as well as what kind of a host system wants to drive it. The reason it depends on the size of the network is that if it requires 2 chips to write, then I think it's a 2 to 4 chips. Then it's a fairly straightforward. But if it requires like hundreds of chips, then we need to address the different latency through multiple chips on the same mesh, and that's a much harder problem to solve. The second thing that really depends on the host. So if you're doing 100 chips in parallel, then we really need a centralized host, depending on whether that host is a CPU, a GPU, another ASIC chip that actually changes the system topology significantly. So speaking of software, I'd like to introduce a little bit our software flow. So imagine you're a potential customer. You have a existing machine learning model that is in a TensorFlow or on PyTorch. So the first step is to convert them into the standard ONNX format, so that our SDK can convert the ONNX into our into the intermediate representation that can be run on our chip. So the ML model quantizer tool, it transforms the standard machine learning inference model, which is typically 32-bit floating point tensor and operators. It translates them into 8-bit tensors operators, and while minimizing the expected accuracy loss. And in the chance that, as I mentioned before, if we want to recover some of this accuracy loss, we can kind of go back and perform another step, which is a quantization aware training. This is contingent on the customer actually giving us the full data set for us to enable the quantization aware training. So after the quantizer, we have the ML compiler. The ML compiler basically takes the quantized network model representation and it maps the ML operators to the accelerator hardware or to the on-chip NPU. So for example, a convolution operator or a matrix multiply need to be enrolled to a vector matrix multiplication that can be mapped to our NPU, and it needs to allocate the storage, figure out whether we want to map this in a memory constraint or a power constraint fashion, and it needs to generate the C++ program, which will eventually be run on the RISC-V processor. And lastly, we have a deployment tool. So the deployment tool really translates all this into the weight of the neural network and into the kind of the RRAM value and the application wrapper that's needed to program the RRAM device so that it can behave and perform this neural network inference. It also generates the executable code for the RISC-V CPU. In this case, it's called the ELF file. And all of those are kind of loaded into the either into the system memory or into the bootloader memory. So these can be booted by the CPU. Even though internally it's a very innovative architecture using RRAM for in-memory computing, but externally, we still need to interface with a standard like a software deployment and the development flow. So it's a standard set of a C++ library that is run on a fairly standard instruction set CPU that takes into account some of these complexities or algorithms that's needed in order to deploy the machine learning model on the RRAM device, which is packed into a different number of NPUs on the edge device.
So do you imagine deploying this in data centers or in sort of real world devices or both?
Yeah, actually, this actually leads us to the next slide. So we kind of like to think that kind of a so-called three waves of production. So we talk about our 65 nanometer chip MX100. So I'm very happy to let you know that currently we're developing on the next generation 22 nanometer chip. which will go into production this year. So in the 22 nanometer chip, this is actually this is actually mostly serving the edge inference market. And this is because in order to go into the data center, we really kind of need more advanced technology nodes. But in 22 nanometer, will do great in the edge inference market. So think about your headsets for audio applications. Think about your security camera, smart camera. Think about your IoT device that goes into sensors, televisions, fridges. Think about the industrial IoT, like a meter reading or a water meter or gas meter, and think about some of the smaller scale, like a small language models. So these are the edge inference market that we're really trying to address and capture a big part of this market with our 22 nanometer chip that can deliver the low power, high throughput, low latency, and high adaptability. We do believe that in-memory computing is a fundamental technology. It's a very disruptive, and it has a strong potential to be deployed into data centers. But to be deployed into data centers, there are a few problems that we need to solve. Number one, as I mentioned, is the accuracy. So even though 8-bit is sufficient for our inference applications, but in a lot of data centers, we really need a higher accuracy. Number two is to have that go back to the SDK. So currently our SDK is optimized for inference. So in order to go to, for most data center chips, the requirement is actually you need a chip that can do both inference and the training. In the existing market, there's a very little appetite for an inference only chip for data center because most of the cost and the bottleneck is actually in training. And if a model developer has trained a model in a particular chipset, there's usually very little incentive to perform inference on another chip because a lot of time it means that they have to rewrite a lot of that library, and there could be accuracy loss. So to go to the data center market, we need to figure out the inference flow on both the hardware and the software level. And this is something that we're not quite ready yet at this point. And lastly, to go to the data center market, we really have to run much larger models. We're talking about models on at least on the order of 10 billion. That's the kind of the minimum bar to start off as a data center market. Whereas for the edge market, we're able to entertain an extremely large segment of the edge market with like a megabytes or tens of megabytes level models.
A question from the Zoom audience. Most ML models are mixed precision with INT8 or FP16 layers. Does it support floating point operations? So I think you had spoken earlier some to that, but I'll let you answer the question.
Sure. Yeah. Thanks. Yeah. So the question was a lot of the ML models are mixed precision INT8 and the FP16, and what do we do with the FP16? So it actually depends on the application. In our experience, a lot of the vision models can be entirely quantized to INT8. It's possible there are some very small inference accuracy loss, but in almost all the case, not only with TetraMem, but kind of with the industry at large, the vision model deployment is trending towards INT8. For some of the audio models, it's possible that some of them do need 16, and we do have support for a 16-bit activation. Yeah. No, it's okay. Yeah, go ahead.
Okay, so I know you talked about data center over and over. That's okay. Not like, don't take it as criticism. It's a conversation. I know you talked about data center, but what kind of interconnect are you going to use to connect to I don't know, more commonly deployed data center or hardware platforms?
Right.
That wasn't very clear to me, so
Sure.
just one question.
Yeah, great. So the question was, what kind of interconnect do we need in the data center market? To be totally honest, right now we're predominantly in the edge market. So we don't have a I don't have a firm answer. Again, the answer depends on I think the answer depends on the system architecture. For example, PCI Express, InfiniBand, and NVLink are all possible solutions. And increasingly in data center, there's a growing demand for optical interconnect. So really the answer to that question it depends on how many chips we need to scale out and whether um and whether worst case, like whether we need to guarantee worst case latency. So number one, how many chips do we need to scale out? A lot of if we just need to scale out to 100 chips, then PCIe, Ethernet, it kind of really doesn't matter. They all work. But if we need to scale out as OpenAI does to like a 50,000 GPU cluster or hopefully 50,000 TetraMem chip cluster, then really it needs to be this I think extremely challenging effort in and out of itself. The second thing that it dictates in the data center interconnect is that whether we primarily need bandwidth or whether we primarily need to guarantee latency. So a lot of the mission critical systems, if we need to guarantee latency, then it's kind of a different solution. Whereas if it's just a bandwidth, it's a different interconnect.
Can I ask a second question?
Of course.
Okay, builds upon the first question to some extent. So I know this talk focused mainly on ReRAM and all that, but don't take it as criticism, but it was a little like what should I say, lighter on the computer architecture side, which is my personal interest.
Cool.
So I was just learning your company's product on my phone right now as I listen to your presentation, of course, and it appears that it's basically you license Andy's technology RISC-V core, and you must have some kind of proprietary computation array to do that in-memory compute. Is that basically what your SoC? Because you didn't talk much about how you did the SoC part, which will be interest to me. But can you comment on the internal architecture a little bit?
Sure. Yeah, definitely. So in terms of architecture, yeah. So the question was, what does our SoC architecture look like? So in terms of major blocks, there's really in terms of compute, there's really three things: the scalar, the vector, and the matrix compute. So both the scalar and the vector, we use like existing third-party IPs. In this case, the public announced one is Andes. So Andes provides us with a solution for a CPU for scalar and a vector agent for vector processing or the DSP processing, and our proprietary APU performs the matrix processing. So in terms of compute, scalar and the vector goes to standard, Andes, and matrix computation goes to our APU. In terms of data transfer, there's actually a significant for AI chips. There's actually a significant. It's extremely challenging problem to solve, which is how to increase the memory bandwidth and minimize the memory traffic. So in this case, our most CPU vendors, in the case of Andes, provide an industry standard memory interface. In this case, AXI. We have found that there is a need for us to develop our own internal on-chip memory in order to both reduce the latency for memory access, as well as the increase the on-chip memory throughput. So most scaled out AI chips have some kind of proprietary bus that's optimized for memory traffic, and we have that innovation as well. And in terms of the interface, it's fairly similar to an Edge IoT device interface, so used by JTAG, UART, GPIOs.
Okay.
Great. Yeah, thanks for the great questions. So with yes.
Sometimes people in the audience ask for a copy of the speaker slides. At the bottom of the meetup, there's a comment section. If you get a chance, if you could post a link to a PDF of your slides, that would be
okay.
Of interest to the audience.
Sure. Yeah, we'll do. Yeah. So I think so we've built a very strong team to develop RRAM-based in-memory computing solutions for AI applications, and our founder team has been working on this for more than a decade. And our team consists of leading experts in AMC device architecture and the industry veterans with a strong track record of silicon execution. So to be the kind of ultimate intelligent solution providers, we need to innovate on the entire stack, from the device to circuit to the algorithm and the application. And you know, we are very proud of our accomplishment that have allowed us to build this extremely high energy efficient chip for our edge device. And we look forward for the opportunity to kind of scale out this architecture and eventually one day to go into the data center market. And a little bit of news, you know, actually this was just announced today or yesterday. So EE Times, which is a very prestigious journal in the field of electrical engineering and electronics, they've recently published the 100 startups to watch in 2025, and we are very honored to be on the list in the field of edge AI devices. So so if you are interested in some of the work, thank you. So we're very honored to be recognized by EE Times in my opinion extremely prestigious and a competitive category for AI inference chips for edge device. So feel free to check out the article that kind of talk about you know what EE Times believe is the industry trend for hardware in this year and the next few years, and why some of the companies are selected and kind of their vision how the industry is evolving. And last but not least, you know, we're hiring. I like to say because our memory is too fast to wait. So in Silicon Valley, in terms of the engineering team, we're hiring for both the hardware and the software design. For hardware design positions, we're hiring for analog, digital design, and the verification engineering positions. And for software designers, if you're passionate about building machine learning models, we are hiring ML engineers to help us kind of either develop or customize some of the machine learning models. And we're also hiring software engineers that will work on compiler, runtime, and SDK, so that those machine learning models, either developed internally or externally, can be deployed efficiently on our hardware. And yeah, so thanks for the opportunity for this talk. This is a QR code for our company. If you'd like to scan it, or you're welcome to connect us on LinkedIn or any other you know, social networks that we have a presence in. Yeah, thank you for the opportunity. Happy to take any questions. Yes.
Can you talk a little bit about how a similar architecture would go from inferencing to learning? So that's a lot more of a dynamic environment, right? That things come in and out of memory. I mean, what you're saying is effectively pulling in the data, you replace the cache with some on-chip memory, and that is more or less static. So it's, if you're in a learning environment, it will always be like a dirty cache, and that's the problem they try to solve. How will this architecture, can it ever really address that?
Yeah, so the question is, I talk a lot about the inference. So what about like in a learning environment? To be honest, I'm not the best person to answer this. I think our software architecture lead will have more insight. From a product perspective, most of the times we rely on existing trained and learned machine learning model, and we just focus on the inference part. Yeah, it's not something that we have yeah.
To respond to the audience question is if they could do post-training, post-quantization training, then if they're using the model over time, over like a number of months, and there's some drift in the behavior of what's being observed by a vision model or something, then they could probably get updated images and do the same kind of post-quantized training. So to adapt to the data drift of how things are changing in the environment.
That's right. Yeah.
So they've already mentioned they have that feature.
Yeah.
So if it's not a radical change, it's something that they could probably do to adapt to the environment.
Right. That's right. Yeah. That's right. Yeah. Thanks for the edit. Yeah. So once deployed, we do have the ability to update the weight and update the algorithm with the so the algorithm needs to be adapted. Yeah.
Do you use your own hardware to do any AI tasks for your own work making the chips? Yeah,
the question was, do we use our own hardware to do any AI tasks? So currently, this hardware is used for like edge IoT applications. Most of our hardware, I mean, in terms of like PCs, or we use a lot of like PCs or design servers. So yeah, currently not.
So if we wanted to kind of, for like a larger data sets, pipeline them, what would be the interconnect or cascading strategy? Like you said, NVLink, that we can understand, but what about others?
Right. So the question was if we have a larger data set, what was the interconnect strategy? I think this is a little bit similar to the previous gentleman's question on the interconnect for data center, which I've answered. So maybe I'll answer interconnect for edge device.
Data center is a larger one, right? But
Right.
I want just 5 of the
Right.
data center.
Right. So for edge device, our standard interconnect include like a QSPI or a JTAG. So most of these edge IoT interconnect do allow for a multiple device to be connected to the same master up to like maybe 5 or 20, depends on the protocol. So we are able to deploy like anywhere less than 20 device on the same board fairly easily. The more challenging part is that if a host, if all 20 chips kind of behave as if they're standalone, we just need a host to send data and dispatch instructions for them. That's a very easy programming model. The much harder programming model is what if we need each chip to see other chips like a memory and a memory content? That becomes a much harder programming model. And in that case, we really need to work with the system architect and the customer. Depends on what host they're using and what's the programming framework. Yeah.
My question is about the resistor, the quality and reliability of durability, temperature, variations,
Right.
aging.
Right. So the question was on the reliability of the RRAM device, like a reliability and aging. Okay, so in short, the RRAM device actually has a very good retention and endurance compared to other memory device. And the reason it is the case is the following: is because RRAM device operates based on building this conductive filaments, and this is actually driven by ions. Whereas most of the circuits that we know are actually driven by electrons. So as you know, ions are heavier. There's different materials that can be used to build the RRAM device. Some are heavier than others. In general, the heavier ion it requires more active conversion energy to move it, which means the device has a better retention. The trade-off is that it requires more energy to write into it. It requires more energy to try to change its state. So TetraMem develops a multiple material stack, and we work with our foundry to kind of optimize that. But as a commercial device, it needs to be subject to the same kind of memory requirements, like H-tau test, high temperature data retention, low temperature data retention. It is subject to the same like a JTAG standard as the other memory. And yes, we believe RRAM device can pass those the same stringent requirements.
So temperature dependency, the value of this.
Yeah. So the question was whether the resistance of the RRAM cell has any temperature dependency. The answer is yes, and that needs to be modeled and compensated so that the MPU is robust across the temperature. Okay. All right. Thank you.
Congratulations again on your award.
Thank you. Thanks. It's a pleasure to give you this talk. Feel free to add me on LinkedIn, and and I'll reach out to me if you have any more questions. I'll be staying around a little bit if there's any more questions. Yeah. Thank you, and I'll stop the Zoom for those who's online.